So welcome to video 5 in B04, our short introduction to Python. So now we're going to look at functions, both inbuilt functions and ones we can actually write ourselves to do particular tasks. So an example of a function is the function help. So if we have an interest in a particular function like len, which gets the length of a list, we can type in len inside these round brackets here inside help to get more information on that particular function. You can also search for it on python.org or indeed search for it at this link here, docs.python.org for /3 for Python 3. So if we have a function len that gets the length of var1, if we assign var1 to be equal to the value u, it will tell us that the length of var1 is equal to 3. In the same way with the input function before, so if we ask a user, say, to enter in a DNA sequence, and we can assign that as an integer, we can then report that back to the person. So here we're just taking an input string of letters and then assigning that to as an int, and we can do things with that after that. So an example of that is that we can print the length of my DNA, the DNA sequence. We can then divide by 3 to see how many potential codons it could have if it's coding sequence. We can also get the actual number of codons if we take len DNA modulus 3 to see how many remaining bases will be left over. We can make this more concise by creating a list out of it and getting the length of that. And we could print this out to say what that length is. Of course, there's a lot more to this that we have to check for. That each of the letters is a nucleotide. Where's the stop and start site? What type of stop and start codon is present? And then the amino acid translations. There's quite a lot of steps. We can see how these commands can be useful. So if we want to create our own function, we have to use the special command called def to define our own function. And we can give it any name. So I'm just going to call it my function 1. There's an arbitrary name used here with round brackets and the colon at the end. So the colon dictates that code is going to happen next. And then we have our function. So there's a few things to notice here. We have def here. Then we have our name with the round brackets and the colon at the end. We have our code, 2 lines of code within the function. So we have var1, Alice, Bob, and Charlie, and then print var1 at the end. And we note that our lines here are indented. So this indentation is very important to Python to note these lines are part of this function. The next thing to do is that we want to call this function. So call the function, we type in the function name, and by typing the function name with no arguments are needed, our Python code script goes back up to where that function is, wherever it is in the script, and execute these 2 lines of code within it. So if we repeat my function 1 many times, each time it'll go back up here, execute these lines, and that would mean it prints out Alice, Bob, Charlie over and over again. We can have a different function. For example, you have def my function 2 name. A name is a local variable within this function, and we can print name out. So you might have my function 2, and we might give it the text hal that is sent up to this function. So hal is an argument to this function. It is sent up, and it basically takes on the value of name here, and we print out the name hal. So if I said my function to Danielle, it would go up here to this function and be printed out. So it's not directly printed out by this function, but indirectly it is by the code within it. We can have a variation on this where we have a function that takes on a name. It might do something to that name, but instead it just returns the name. So return is a special command to send this back. So we've got hal is sent up here to name like before. Hal is returned here, and the return action sends it back here. So you get it's returned back to name and it's sent back to v1. So we could do things to the hal text. We could add an extra letters or something like that within our function here if we want to do, but we're just keeping it very simple here. There's important commands here. The def to define our function. We're taking the argument name inside here, which is just a local variable, and using the special command return to return that variable. And then we're sending that to v1, and I should use an equal sign if I didn't like writing the R language so much instead. So apologies for the occasional typos that creep in here. You should be able to detect them, I hope, yourself. Finally, we have this function. So we have my function for, we have our DNA sequence, which you could read in from the user if you want. We send it up to name, return len name divided by 3. So returning the length of it in amino acids, roughly speaking, and that's sent to v1. So that should be an equal sign here when we're sending it to v1, and then prints out v1 is something round v1 comma 2. So we're saying v1 is, and we're rounding that function to 2 digits here. So if we want to think about what happened here, we'd have 1, 2, 3, 4.3. 4.33 is what it would give us. v1 is 4.33. And you can try it out yourself and create your own functions to do different things. Start with something simple, like this one, and then you can build up from there. Other functions that are convenient in Python are to create a numerical data set like this. Might be, readings from an experiment, and you might want to get the minimum, the maximum, and the sum, all of which have intuitive function names, sum, max, and min. There are variations on this if we import the package called statistics. So we put this import command at the top of our script, typically, just like importing packages in other languages, we need to add them in. So the import function is important here. And then we can print out, use special ways of talking about our functions here. So we have x1. So if we want to get the mean of x1, we write statistics.mean, and that will get the mean from x1. So it's effectively calling the package statistics, looking for the mean function, and we're giving it the x1 as the argument to that. And we're wrapping round around this because we don't need the mean value to 75 digits. We just need 2 digits. It's perfectly fine for us. We can get the median as well. We can get the standard deviation too in the same way, just STDEV. So this means that Python can calculate numerical values if we needed to. Another handy package is called random. So random can generate random numbers, one of which is random.c to make a random number. There's other parameters that could be added in here which are not essential. Another handy command is to random.randrange, and that will create a random number between 1 and 10 with a step size of 2. So you can try this out to see what values it would give us. We would also use random.uniform to generate a random number between the values of 2 and 6 as well. So these can be useful for plotting data, or indeed for testing the validity of data that you have in your experiment. Other functions, so another one to generate a range of values is called range. So that will generate from a start 1, stop 12 with the step size of 2. So this will generate numbers 1, 3, 7, 9, 11 in here using this function. Note that it only works with integers, not floats. So if you're looking at decimals, you'll find this won't really work for you, and we'll need to use the NumPy package to do this properly with kind of an array-like structure. So to do that, numerical Python, which is a really great range of tools, we import NumPy, but we call it NP. So NP stands for as a shorthand for NumPy. Okay, so what's important to note is that because we use this special shorthand called NP, we have to call our functions with this at the start. So this is the same in effect as calling the package statistics. We just use the shorthand as NP for numerical Python. So that means we'll use this function called np.arrange, which gives us a more flexible range of values that can use decimal points inside it if we want that. So this suite of tools has a whole range of different functions that are very, very handy. So to install that, what you need to do is go to PyCharm, go to settings, go to search for project, and go to your Python interpreter here, and then search for NumPy in your packages. So you'll find it there, install it. It might take a minute to install. And when you have it installed, you'll see this special signal saying package NumPy installed successfully at the end. So it'll take a minute to do. So again, that's PyCharm settings project, Python interpreter, click on plus to search for NumPy, and then add it as one of your packages in PyCharm. So you'll need that at the top of your script. And what we can do is create a set of values here, start, stop, and a step of 0.5, and send that to np.arrange. So that goes from 1 to 12 with a step of 0.5. You can see it down there, 1, 1.5, 2, 2.5, 3, 3.5, and so on, all the way up to 12. So that's a variation on the original function range. And just note, we've got np at the start. So you can see how that would look in code with PyCharm. I might find this is easier to do in PyCharm than it is on the prompt. Other functions, so we can use arrays in Python, which are very, very handy to use. So arrays are very, very flexible. They typically contain a set of numbers, and they can have multiple dimensions as well. This is just one dimension of 6 elements, but it could be more complex if you want. We can print out our array, A1 here, or we can print out element, the third element here, 5, because it's going, again, it's going 0, 1, 2, in terms of the element indices, 3, 4, 5. So that will print out the value 5. There's other functions in NumPy which are quite convenient. So np.zeros will make an array with a bunch of zeros. np.ones will print an array with a certain number of ones, depending on what argument you give here at the value 2 or 3. Or you can create an empty array with 11 empty elements as well. And that can be handy when you're performing particular tasks to fill up empties into an array. So if you're processing data, these kind of things can be handy to create empty or initial values before you add on the real processed values. Other functions. So we have an initial variable called A1, another one called A5. We can concatenate them together. So this will create a vector 1, 2, 5, 5, 4, 8, 6, 11, 0, 1, 1, 1, 0. All those 12 elements together. We can ask then, how many elements does this new A1 have? How many dimensions does it have? And importantly, how many elements per dimension? So because Python can do multi-dimensional arrays, that means these questions become more pertinent to understand how complex is our particular data set. So you can see here, this is our array from above. It's A5 first, followed by A1, I should say. So you can see the breakpoint here. So we have our np.array there. So here we have another range of numbers. We've got 7 numbers. And we can ask with square brackets, a bit like R, if you ever use that. We can ask what elements within X have values greater than 2.5. So if the square brackets here, what we're saying is that we're looking within X, and we're using X within as our variable within this vector to search for each of these elements. Are they greater than 2.5? So we'll search through this array, and we'll look at 1. Is 1 greater than 2.5? No, it's false. It's not. So 1 is excluded. Is 2 greater than 2.5? No, false, not included. Is 5 greater than 2.5? Yes, that's included. Same for 7. Same for the rest of them. So this will mean we print out X is 5, 7, 11, 3, 4. If we say, what are the even numbers in X? It will do the same thing. So go to 1 and say 1 is odd. It's not included. 2 is even. It is included. 5 is odd. 7 is odd. 11 is odd. 3 is odd. And 4 is even. So it just prints out 2 and 4. So what it's doing here is taking each element and saying, this element mod 2, what is the remainder equal to 0? So this double equals is comparing this value, the remainders after dividing by 2 as many times as we can, to the value 0. If we wanted the odd numbers, we'd say equals equals 1. Finally, we can combine these using the ampersand. So this will now say for each element x, they have to be greater than 2.5, which we know we mean we have 5, 7, 11, 3, and 4. And we also want them less than 7, which means that we're going to get 5, 3, and 4 that satisfy these criteria because both items have to be evaluated as true and true. If we did a pipe, instead that would mean or. So in that case, that would be either of these could be true, in which case we get all these numbers above. There's other handy shorthands which may or may not be useful. So again, if we have an array called x, we can access the first 3 elements of the array by simply typing in x colon 3. So it's like kind of going 1, 2 to 3, and we could change 3 to be any value. It's getting all these elements, the first 3 elements of x, that'll print out 1, 2, and 5. If we had 4 to the end, that will mean it prints out 4 until the very end there. So 7, 0, minus 2, minus 3. If we wanted to get the elements of x that are less than 0, we could put that criteria at the end here with round brackets and use np.non-zero, x less than 0, to print the elements of x that are less than 0 and also not equal to 0. And it prints out the array indices. So that can be handy when you've got complex lists of numbers where you're looking for a particular type. So these are shorthands that maybe might be useful. So note also that this title here at the top stands for n-dimensional arrays in numerical Python. So that kind of concludes this area of a range of functions that we looked at that can do helpful things, and there's many other functions in Python. So we're just looking at a few key ones to help you as you learn Python.